My name is C.N.Ekaputra from Northwestern University in the US, and today I'll be presenting about an aluminum alloy manufactured by laser powder diffusion of blends using both elemental and pre-alloy powders. Before I start, I'd like to thank my collaborators, Dr. David Weiss from Industries, a company specializing in aluminum castings, Dr. John-Eric Magoni from the US Army Research Laboratory, and my advisor, Professor David Junot. So the alloy that we're working with today is this aluminum serum magnesium scandium zirconium alloy. And we designed this alloy for two reasons. One is, of course, printability, and the second is for high temperature mechanical performance, as we want to design lightweight aluminum alloys that can replace heavier or more expensive titanium or iron-based alloys at temperatures up to about 400 degrees Celsius. Now, cerium is an element that has attracted some attention within aluminum alloys pretty recently. And one reason for that is it exhibits this eutectic solidification reaction during cooling, where you form this aluminum and aluminum-11 serum three-phase at the same time. And this narrow solidification range inhibits hot cracking. This is quite similar to aluminum silicon-based alloys, but the key difference is that this aluminum-11 serum three-phase is very resistant to coarsening due to the low diffusivity of cerium in the aluminum matrix. This enables these eutectic aluminum cerium alloys to maintain their strengths at temperatures where aluminum silicon alloys are becoming weakened. Scandium and zirconium are also quite popular for reasons that others have mentioned today and yesterday. This is due to the effective grain refinement of these scandium and zirconium staining precipitates, improving resistance to hot cracking, and the formation of coarsening-resistant nano-precipitous agent. So the idea behind this alloy is that we combine cerium, scandium, and zirconium with additional magnesium for solid solution strengthening, providing an alloy of excellent printability and high temperature performance. Now, the alloy today is manufactured not by using fully pre-alloyed powders, but by instead using this technique of in-situ alloying, which some other researchers at this conference are presenting on. So the idea is that we mix these aluminum cerium 10 magnesium powders and add to it elemental scandium and zirconium powders. We gently ball mill it to achieve a homogeneous distribution, and an alloy takes place during the laser powder bed fusion process itself. Now, the main benefit of this process is that it's considerably faster and less expensive than atomizing fully pre-alloyed powders. But the key challenge is to achieve a homogeneous microstructure. So that will be the focus of this talk. We're going to study the effect of the laser powder bed fusion process parameters and the starting materials on the homogeneity of the microstructure, and we do this through a combination of experiment and modeling. I'll then talk about the effects of this microstructural homogeneity on some other things like the grain size and mechanical properties, specifically the microhardness during aging. So immediately when we print the sample, what we see is that the microstructure is quite inhomogeneous. If you zoom into this gray matrix in the background, what you see is this FCC aluminum phase reinforced by these cerium and magnesium staining precipitates. And this is basically characteristic of the aluminum cerium magnesium alloy without any sort of scandium zirconium in it. Now, when you take a look at these white and gray particles, what we see is that they are indeed undissolved zirconium and undissolved scandium particles. We focus on the right on one of these undissolved zirconium particles, and we see from these EDS maps that it is indeed pure zirconium in the center with aluminum outside of it. And this indicates that very little dissolution has taken place during this laser powder bed fusion process. Interestingly, if we do EBSD around this particle, we see some local grain refinement, indicating that some zirconium must have dissolved such that the concentration of zirconium is high enough to form these aluminum-3 zirconium precipitates, which can then nucleate fine grains. We can also take a look at the phase mapping of this aluminum-zirconium interface. And what we see is a series of aluminum-zirconium containing intermetallic phases, where we have these less zirconium-rich phases towards the matrix. As we press closer towards the center of the particle, these phases become more zirconium-rich. And this sort of structure is very characteristic of zirconium diffusing from the zirconium particle into the surrounding liquid aluminum. Now, of course, these particles are quite undesirable, since any sort of scandium or zirconium locked in these particles is therefore unavailable to form secondary precipitates later on during aging, which provides strength. So the goal now is to vary the laser powder bed fusion process parameters and see if we can achieve a more homogeneous microstructure. So the first parameter that I'm going to talk about is the effective scan speed. And here we keep the laser power, hatch spacing, and layer thickness constant. And I'll also note that laser power is the maximum power that we can achieve on the machine. We then measure the area fraction of undissolved zirconium particles by image analysis techniques. And what we see is that as the scan speed decreases, the area fraction of these particles also decreases, indicating that the amount of zirconium dissolved is increasing. Now, this is quite expected since as we decrease the scan speed, we're increasing our volumetric energy density. We're also increasing the amount of time that the zirconium particle can spend within the melt pool. Now, one might think that in theory, we could go to even lower scan speed and dissolve more zirconium. However, in practice, this severely compromises the integrity of the parts that we build. So we can't really go any lower than this. The other parameter that I'll talk about is the effect of scan strategy, in particular when we scan every layer twice. And what we had expected is that by scanning every layer twice, the zirconium particle is spending longer time in the melt pool, and therefore we achieve greater dissolution of zirconium. However, we see that this is indeed not the case. And our hypothesis is that the absorptivity of the laser powder bed is changing during the rescanning process. When the first time the laser encounters the powder bed, it's encountering a relatively rough surface, so there's multiple reflections that can take place, increasing the amount of energy absorbed. Whereas when the laser is encountering the powder bed for the second time, it's now encountering a more flat surface. More of the laser energy is directed upwards, and the amount of energy absorbed is less. And therefore, it will decrease the amount of zirconium that can be dissolved during the second scan. But at the end of these experiments, we see that we still have quite a bit of undissolved zirconium particles. So we strive to understand the effect of these parameters further and understand what we could do further improve the homogeneity by modeling. So let's consider a simple model. We consider a spherical zirconium particle immersed in the aluminum powder bed, and then measure how much the zirconium particle dissolves as the laser passes over it. And this amount, we do this by numerical modeling. At every single time step in the model, the zirconium particle lose some mass, and it will do so by two mechanisms. The first we consider is the effect of diffusion of zirconium from the solid zirconium particle into the liquid aluminum melt pool. And this we consider by a fixed first law type equation, which we modify by this SH term, the Sherwood number. And this estimates the effect of Marangoni flow in the melt pool. The second term, this melting term, occurs when the zirconium particle is hot enough such that it can melt. And this is simply the melting rate of a spherical particle. The temperature we give by assuming that a laser is a moving point heat source for which you can use the Rosenthal solution, and which we then modify by imposing a maximum temperature to avoid any sort of issues with the singularity when the laser gets very, very close to the particle. So when we put all these equations together, what we do is we fix the location of the zirconium particle, we allow the laser to move towards Twarrell and away from it, and then we measure the temperature during this process, and then we calculate the fraction of zirconium dissolved as a result. We then have to recognize that the zirconium particle can really be anywhere with respect to the laser. And since this position has a strong effect on the temperature, and therefore the amount of dissolution, what we do is we perform this trial many, many times for random locations of the zirconium particle, and then for a given set of process parameters, we estimate how much zirconium is dissolved by taking an average over all these trials. So let's do this now. Let's represent the effect of scan speed. And again, what we see from the model is that it reproduces qualitatively our experimental observations, in that as the scan speed decreases, the amount of zirconium dissolved increases. And you can see that the agreement between the numerical model and the experiment is okay, but the main point is that we're reproducing qualitatively our assumptions. Now when we revisit the effect of remelting, we see that there is indeed no effect. And in the model, simply what we do is we pass the laser over the particle twice, and we're careful to choose the absorptivity such that during the first scan, the absorptivity is characteristic of the aluminum powder bed, whereas during the second scan, it's characteristic of an aluminum flat surface. And what we see here is that there's no effect of remelting. Okay, so after all this, what can we now do to affect the microstructural homogeneity further? So of course, if we can decrease the powder size, that should increase the rate of dissolution of these zirconium particles, but also if we can lower the melting point, then we can use a melting mechanism which is faster than the solid state diffusion process. So our choice was to replace these elemental zirconium powders with so-called master alloy aluminum 10% zirconium powders. Now you can see that the difference is that these aluminum 10% zirconium powders contain these micron-sized aluminum 3 zirconium precipitates, which are considerably smaller than the pure aluminum particle, pure zirconium particle. We also know that the aluminum 3 zirconium phase also melts at a lower temperature, so this should also help our dissolution process. And indeed, when we revisit our model and model the effect of particle size and starting material on the fraction of zirconium that can be dissolved, we see qualitatively that there should be an effect by decreasing the powder particle size and lowering the melting point. So we revisit this process. where we produce these master alloy powders. And by the way, we don't do this by atomization. Instead, what we do is we arc melt together pure aluminum and pure zirconium, and then pulverize this using a high energy ball milling process. So we produce these master alloy powders, again mix it with the pre-alloyed aluminum magnesium, and then print it. Both these samples that I show here are produced with the same processing conditions. And what you can see from the micrograph on the left is that this microstructure is considerably more homogeneous than what we saw in the beginning. It's not perfect. You can see some of these white regions, which are pockets of concentrated zirconium, but there aren't any of those pure zirconium, pure scandium particles. We can also measure the concentration of zirconium dissolved by EDS, and what we see is that concentration of zirconium dissolved by using these pre-alloyed 10% zirconium powders is higher than when we use these elemental powders. And by the way, I focus on zirconium here, but all these observations also extend to scandium. Now, as a result of this greater dissolution, what we see is that there's greater grain refinement in the alloy containing these pre-alloyed 10% zirconium powders. This is, of course, due to the fact that we're able to dissolve more zirconium during melting, which is able to nucleate fine Lu-3 zirconium precipitates, which can then nucleate fine grains. And in the elemental zirconium, when we use elemental zirconium scandium powders, we only saw this grain refinement in the vicinity of these undissolved particles. Lastly, I'll talk about the effects on microhardness during aging. And when we take a look at the the sample producing elemental powders, we see no effect when we compare this to the base alloy without any sort of scandium or zirconium, owing to the fact that very little was dissolved during the melting process. Now, when we replace it with these pre-alloyed powders, we can measure a hardness increase during aging due to the fact that we have more zirconium dissolved, able to form more secondary L12 nanoprecipitates, providing an increase in hardness. So, in summary, we manufactured this aluminum serum magnesium scandium alloy for high temperature applications by this process of laser powder diffusion of powder blends. When we use elemental powders, we saw that these powders were only partially dissolved. And then we studied the effect of laser process parameters, such as the scan speed and rescanning strategy, on the effects of the zirconium and scandium dissolution levels. And we did this by both experiment and modeling. We then replaced the elemental powders with master alloy powders, and this resulted in greater microstructural homogeneity and an improvement in mechanical properties. And lastly, this approach should not be limited to just this alloy, but should be also extended to other alloys manufactured by similar processes. I'd like to thank my collaborators one last time, and thank you. I'm happy to take any questions.